Today we're continuing the money button documentation series. We're talking about not just money button, but also sort of the details about how Bitcoin works and how to use our library BSV to do all the sort of Bitcoin related functionality you need to make advanced applications. So today we're going to talk about ECDSA, or elliptic curve digital signature algorithm. And I'm going to share my screen, and as usual, guys, I can't see anything when I share my screen, so just let me know if something goes wrong. Okay, you should be seeing my presentation full screen.
Yes, perfectly.
Okay. All right, so ECDSA in a nutshell is we're going to talk about basically an overview of what we're talking about here. What are signatures, digital signatures? A bit of mathematical preliminaries, so just a bit about prime numbers and things like that that's sort of related to this. We're going to explicitly compare DSA to ECDSA, which are two different ways to create digital signatures. ECDSA is what's used in Bitcoin. DSA was first, and it's in some ways it's a little bit easier to understand, but it's also extremely similar. So it's just interesting to compare and contrast them. And so part of that will mean looking at what is the discrete log problem, which is sort of the foundation of what makes this stuff secure, as well as the discrete log problem, which is the same form of that, but with elliptic curves. And then after all that stuff, we'll talk about something called deterministic K, or RFC 6979, which is a way of creating deterministic signatures. And so we'll explain what all that stuff is. So first of all, the idea is that we want to have a digital form of signatures. Like when you have a contract with someone and you sign it, the idea is to create some type of digital signature so that you can sign a file and have a signature that cannot be forged. And so the idea should be something like, well, first of all, it ought to be economically infeasible to forge a signature. It ought to be basically impossible for anyone, including very well-resourced attackers, to be able to forge a signature. So that means it's going to be based on asymmetric cryptography, where the signer has some type of private key that only they have, and other people can see the public key. And so if they know that that person owns that public key, when they sign something, they can verify that only whoever had the private key was able to produce that signature, and they're able to do it in such a way that they can't recover what the private key is. And if we had something like this, we could use it for all sorts of things. So data integrity, that just means basically, if I give you a file, you can know that you have exactly the file that I gave you because I sign it. And if a single byte changes, then the signature is no longer valid. So you can sort of guarantee the integrity of data that way. You can know that it came from a particular person. So if I give you data and I sign it with my private key, you can know that it came from me by verifying my public key. It's non-repudiable, meaning basically if I sign something, the signature is always good and I can never take it back again. And of course, you can also use it for digital cash because this is the very foundation of what a Bitcoin is signing transactions from one person to another. So a bit of mathematical preliminaries. So again, we'll compare DSA directly to ECDSA sort of throughout this presentation here. So DSA stands for Digital Signature Algorithm. This was sort of a slightly earlier way to create digital signatures based on private keys and public keys, where the private key is a number and the public key is just a bigger number, basically. And it's based on really just basic arithmetic, prime numbers. So you have to know a little bit about prime numbers. So any number, of course, can be represented as unique product of primes. And you have to know something about modulus arithmetic, which is we can simply define an operation whereby when I multiply two numbers, I can always take the modulus, which is basically I take the remainder over p. And in the case of elliptic curve cryptography, p is always a prime number, a large prime number. And then there's something called Fermat's little theorem, which is a couple of different ways to write it here. Basically a way of, it's just sort of an identity for modulus arithmetic that is used inside some of the proofs that are related to the digital signature algorithm. So there's nothing intrinsically wrong with digital signature algorithm, but that's not what's used in Bitcoin. It has like a minor irritation, I would say, which is that the key size is bigger than you would prefer. And there's a different algorithm called ECDSA, elliptic curve digital signature algorithm, very, very similar to DSA. except that basically because it's on elliptic curves, and we'll see a bit about how this works, the size of keys is smaller. So your public key ends up being a point rather than a giant number. And so the whole thing is very similar, but based on elliptic curve mathematics instead of this modulus arithmetic, although you still have a bit of modulus arithmetic that shows up. So if you were to multiply two big numbers, you end up taking the modulus over something called n, which is the order of the curve. So, okay, a bit more about mathematical preliminaries here. So there's something called the discrete log problem, which is what the security of all this stuff is based on. And so there's two different discrete log problems that are relevant here. So there's the first one, the simple one, which is, I've got it written there in a sentence there. Find A such that capital A equals little g to the power of A mod P. And it turns out that this is basically very, very difficult. So if you were, basically if it weren't modulus, you can actually find little a very easily. You just take the log. But because everything is modulus makes it intrinsically more difficult, and you can't easily find little a. So that's just called the discrete log problem. This is a bit about what these numbers are because they show up inside the math there. So So P there is just a prime number that's 1,024 bits in the DSA spec, although today P would actually be a bit more like 2,048 bits because the original standardization of DSA was from 1994, which is 25 years ago now. So it's basically a bit out of date, and you have to use larger key sizes now to basically secure against faster computers, because computers have gotten a lot faster since then. And then A is your public key, which is a 1,024-bit number, and little a is 160 bits, again, according to the original spec, although, again, today you would have slightly larger key sizes. Okay, so now we can compare that directly to the elliptic curve discrete log problem, which is very similar. Instead of having this modulus arithmetic, the goal here is to find A, little a, such that capital A equals little a times G. And this turns out to also be very, very difficult, with the primary difference here being the key size is smaller. So in this case, G is just a 256-bit value, X value of a point. It is an X and a Y, but you can derive the Y from the X. And so it's a little bit smaller. More importantly, the public key A, capital A, is also only 256 bits. And again, it's the X value and then 1 bit for whether Y is odd or not. So that's 256 bits versus 1,024 bits. So roughly speaking, in this case, basically exactly 1/4 as big, except for that odd value there, odd 1 bit there. But then also the key size in today, in order to have the same security for as elliptic curve cryptography, you'd probably have to use more like 2,048 bits. So it's roughly speaking 1/10 the size. So the key size is substantially smaller. So because the public keys in the case of Bitcoin have to go on the blockchain, you can clearly see that you literally save money by having smaller key sizes. Okay, one more thing here on the mathematical preliminary. So this is just a brief explanation of why the discrete log problem is difficult. So something that is easy is if I have capital A as a prime number and then G to the power of A, little a, I can just invert that and find little a easily with a log. And we have quick algorithms for doing logarithms. So finding the log of a number is a solved problem. You can do that very quickly on a computer, even with big numbers. And then the second thing that says easy there, that's just a typo. That should say hard. I'll have to change the slides before uploading this. But the second one is supposed to say hard. And what's not easy, what's hard, is finding capital A such that G to the power of A mod P is, find little a for solving that equation. Again, there's another little typo there. Maybe I'll just, since you guys are looking at this, let me fix it just because it's going to be confusing to people if I don't fix the little typos there. So what this is supposed to say here is this is supposed to be hard. And then this is supposed to be G to the power of A.
Meanwhile, may I ask, so
Yes.
ECDSA allows to do same like using big numbers, but using less power computation because they're not as large as they used to be?
Yeah, so the size, it is, in terms of actually signing something, I'm not sure whether it's faster or slower. It's probably about the same. It's mostly the size of the storage space that you have to have for the keys. So your public key is about 1/10 as big with ECDSA versus DSA. So it's mostly the storage space. As far as how difficult it is to actually compute the signature, I'm not sure what the difference is in that case.
Okay, so it's not power computation, but you use less, and so the storage space is lower.
Yes, storage space is definitely lower.
Okay.
Okay, so now the math here makes a little bit more sense. So basically, you can't just take the log of that value on the right. I mean, you can define it, but it's not like there's an algorithm for just taking the log anymore. All of a sudden, there are no good logarithm or no good algorithms for this. And in the case of the prime number approach, which is what I'm showing here, there are some algorithms that's better than just randomly guessing. But in the case of elliptic curves, it's pretty much just random guessing. So that's a nutshell of what is the discrete log problem. And this is what secures your private key. So there's just something about modulus arithmetic, and I don't have a good intuitive explanation of this, but something about modulus makes this significantly harder.
Probably I can make a comment about that.
Sure.
Basically, it's not easy to have the inverse operation from modulus, because when you do the modulus operation, you lose a lot of information, basically. Yeah. So that's the problem. You have to start to guessing because you lose a lot of information about the original number, basically.
Yeah.
So I understand it's related to that. That's why it's a lot harder.
I think so. It would be interesting to look at it from like an information theoretical point of view, because it's basically true. When you have modulus, you have these numbers wrapping around, and you have no idea how many times it's wrapped around. So you actually do lose information. That's a good way of looking at it. Okay, so this is just an overview of the idea of DSA, and so this doesn't give you any of the details, but it gives you an overview of what you kind of need to do as an engineer who's programming stuff like this. You'll have an algorithm for creating a signature and an algorithm for verifying a signature. And you have a message that you want to sign. You apply the secure hash algorithm to it, which what that is SHA-1, because way back in 1994, that was considered like sort of state-of-the-art secure hash algorithm, and they actually called it that. And then you have a private key that you use to produce a signature, and then you get out of that a signature. And a signature is an R and an S value, which we'll cover in a second. Meanwhile, there's a different algorithm called signature verification. And the way this works is somebody gets a message from somebody, hashes it, then takes the signature and the public key and performs a signature verification algorithm. And then you get back either yes or no. So you can tell whether a signature is verified or not. And now I took this photo or this graphic directly from the original DSA standardization spec from 1994 in NIST. It's NIST something or other, some standard. And so that's where the photo comes from. Now I modified it slightly for ECDSA, which is basically almost the exact same photo still applies for ECDSA as it is used inside Bitcoin. If you look at the ECDSA spec, it still uses SHA-1, but because in Bitcoin, we don't use SHA-1 really for anything in Bitcoin. We use SHA-256 or double SHA-256. So with only that minor difference, the graphic just about perfectly applies to Bitcoin, as well as when you read about ECDSA, almost all of it applies directly, except that you should be aware that we may be using a different hash function or a different curve than what you read in some of the specs or in some of the other descriptions. Okay, so here's an actual overview of what are the actual algorithms themselves for producing and verifying a signature. I don't personally have a very good intuitive understanding of this, so I can't explain it. I will say that there are proofs that it reduces to the security of the discrete log problem. So long as nobody figures out a fast way to solve the discrete log problem, these are secure in the sense that basically no one can forge a signature. And on the left here, we have, it's pretty easy to look at the math there and see what is R and S. It's just some modulus arithmetic over P and Q. These are parameters on your curve. There's a number there called K. So what I'm not showing is sort of the preliminary description that explains what the numbers are in these equations. But all you need to know about K is that K is supposed to be chosen randomly each time you create a signature. So when you create a signature, you hash the message and so on, and you follow the algorithm. But before you do that, you have to generate a value K randomly. And K is, in the case of DSA, it's actually, I forget in the case of DSA. I'll say in the case of ECDSA, it is simply a 256-bit big number, like the other big numbers in the algorithm there. I can't remember whether it's what size key it is in the case of DSA, but in any case, it's just supposed to be chosen randomly. And this matters because we'll come back to this in a minute and talk about sort of the significance of that. But you can see basically the idea here is you simply find R and S from the private key and the data and the parameters of your curve, or in the case of DSA, it's the sort of numbers that are chosen, prime numbers basically. And then there's a corresponding algorithm that basically plugs in the signature, and you want to basically compare that some of the values come out to be correct. And you can see in the DSA one there at the bottom, it says make sure V equals R. And then in the same case with ECDSA, it's the same thing, make sure V equals R. Now, I show both of these on the same screen because I don't want to spend too much time on it, but if you actually compare every single line, like what are you doing in DSA and then what are you doing ECDSA, they're actually almost exactly the same, except that you're doing it on an elliptic curve instead of with prime number modulus arithmetic. So basically, mod P gets replaced with point multiplication, and that's basically it. So it's because of the sort of efficiency of the size of these elliptic curves that you can do stuff more efficiently. But the algorithm is actually pretty much exactly the same. In fact, I'm not even sure there is a difference. When you compare it one at one, it's like basically just translate DSA into the language of elliptic curves, and it's exactly the same algorithm. Okay, so in summary, so ECDSA is pretty much the same algorithm as DSA. And then the other caveat here is that if you look at how ECDSA is normally defined, be aware that we use SHA-256 instead of SHA-1, like you see in many of the specs. Okay, so a final point here about ECDSA, something called deterministic K. There's a standard for this called RFC 6979. So there's a problem in the history of Bitcoin and other areas of sort of applications of cryptography as well. The problem is K has to be chosen randomly every single time you produce a signature. And this has a number of issues. One of them is that, first of all, when you write code that does this, it's hard to test because your signatures come out different every single time. So you can't have standardized test vectors where you know your algorithm is working correctly. The other problem is that, perhaps more significantly, there's no way to know whether you're producing a unbreakable signature because your entropy pool might be broken. And this happens a lot throughout the history of applied cryptography, where you're basically using a library or who knows what, or an operating system where it gives you terrible random numbers. And if it's giving you a terrible random number and someone can predict the value of K, they can rederive your private key. So it's a problem. It would be nice if you didn't have to worry about this. And there's a way to do this, because it's not that K needs to be literally random. Rather, it simply needs to be unpredictable by an attacker. So the solution here is you generate K by HMACing your private key with the message. And so this has exactly the property that you're looking for, because basically no one can invert HMAC to know what you plugged in there. And so by HMACing the message and the private key, you generate a unique value of K for every message that you sign. But also, so long as you keep your private key private, no one is ever going to figure out, what you put in there. So they have no idea what value of K that you use, so long as you keep your private key private. So it still has exactly the properties that we're looking for, but it's easier to test and it's easier to know that it's working. You can have standardized test vectors where you make sure your code is producing exactly this signature byte for byte. And that's basically it. Okay, so that's all I have for the sort of the theoretical overview there. And then I can show some, I'll show the code in a second here, but then as usual, you guys have any comments or questions before I go into my terminal and start showing off examples?
Well, I do, and I'm sorry if I'm making you repeat stuff, but can you explain to me HMAC?
Sure. Sure. Let me explain that to you by going into the terminal, because it's going to be a lot easier if I literally show the code for HMAC. So let me do that. Okay, and then for people who are wondering, so HMAC is something that we covered in the hash function stuff. So that's where we kind of glossed over a lot of the details of hash functions. But I'll show you what HMAC is right now. So first of all, let's suppose I have some data. I'll say, var data equals, this is my data of any sort here. Now, let's suppose I want to hash this value. So I say something like, my hash is, I'll say, in this case, I'll just do oh wait, I need load BSV first. My data is bsv.crypto.hash.sha256 buffer.from data. So I just hashed this data. Now hashes have the property that if I give you this hash, you have no idea what value I hashed. So it just looks like random gibberish to you. But if I were to give you the value, you would be able to confirm that it hashes correctly. So you would be able to produce the same hash. Now, there are cases when I'm going to be very tempted to do something like this, where I want to say something like data equals, this is my data, plus some other data, and then hash that thing. And I don't want to explain all the things, but in the case of what we're doing here, like in the case of what I just described, what we have is we have two pieces of data. I'll just say data1 equals my private key, and then var data2 equals the message I am signing. And so I have two pieces of data. Rather than just concatenate them together and say like, var data3 equals data1 plus data2, I'm not going to do that. That's a typo, but I'm not going to press enter anyway. What I'm going to do instead is I'm going to do HMAC. So I do, var HMAC equals vsv.crypto.hash.sha256 HMAC, let's say, because you have to pick which HMAC you're doing. And in this case, I'll do buffer.from data1, buffer.from data2. And basically, all you need to know about HMAC is that it's a hash function that whenever you need to hash two pieces of data together, you should use HMAC. And so that's basically all it is.
Okay, great. Can you mash more than two pieces of data?
You can if you want to do something like you basically do it again. So if I wanted to do it a third time, I would say something like, do bsv.crypto.hash.sha256 HMAC on the outside, and I would say my first piece of data would be something like buffer.from. I'll say actually it's more like a third data. And then that would then contain the other one. So that would be a way to combine any number of pieces of data together by chaining HMACs together. Okay.
Okay,
right.
Great, thanks.
Okay. So then now I'll demonstrate. So that is happening inside of deterministic K. So that is inside what I'm about to do. So let's suppose I generate. So what I'm going to do now is I want to actually sign my data. So I'll say something like, again, I'll just as though I'm starting over here. Var data1 equals my data, whatever it is. Now I'm going to sign this. So first of all, I want to generate a new private key equals bsv.crypto.private. Oops. I think it's just .private key .from random. Okay, now I'm going to generate my corresponding public key as well. So I now have my private key and my public key. Now what I can do is I can make my signature. Signature equals bsv.crypto.ecdsa.sign actually, before I do that, I actually have to hash the data. So our ECDSA class doesn't actually hash the data for you. So I'm going to hash my data first. So I say something like bsv.crypto.hash.SHA-256 buffer.from my data. And then the thing that I sign is actually the hash. So there are multiple different hash functions involved. I'm hashing the data itself, and then inside, when it computes K, that will also involve an HMAC, which involves SHA-256 as well. So lots of different hash functions going on. But in any case,
just a comment. The name of the variable was data1, so probably it's going to fail when you verify if you use data.
Thank you. Okay, so var sig equals bsv.crypto.ecdsa.sign. Now I type in my hash first, followed by my private key. Now I have a signature. So that's what I do to sign something. And a minor caveat here, which is that it's kind of irritating that you have to create the hash first, but actually you probably shouldn't be using the ECDSA class directly ever anyway. We have other convenience classes that we'll talk about later. Like when we use, basically if you're actually signing arbitrary data, you should probably be using the message class. Message is a standard way of formatting the data that you signed, hashing it for you automatically, and producing a standardized signature. So we'll cover that in a different video. So this is kind of low level. So you wouldn't normally use the ECDSA class directly unless you are very sure that's what you want to do. But in any case, now that I have my signature, I can check it. So if somebody else has, say, I give to someone the message, they can compute the hash themselves because they just run it through the same hash function. I give them the signature and I give them my public key, and it verifies the true. So if I were to do something different, like, I don't know, let's suppose I give them the wrong public key, just for example, just to prove the concept here. If they have the wrong public key, then that would look something like, I'm going to just generate a new private key right here. So I'm generating a new one randomly. And now if I see if it's verified, it is not verified. And the same thing would be true if I had like an invalid signature or invalid data or something like that. So it only comes out to be true if you actually have the signature and the public key match the data, basically. Okay, so that is okay. So the one more thing I want to briefly mention here. So let's suppose I go back up here and I do my sign thing. So I produce my signature by signing it, and I'm going to cheat slightly here, and I'm going to get rid of that and say .toString. Now every time I sign it, I get the same signature. It's deterministic. That's because we default to using deterministic K. There's a convenience method called sign random K, which uses K randomly. Now every time I sign it, it's a different signature. You do not normally want to do that. I actually added, so that we already had it kind of built into the code and it wasn't convenient. I added a convenience method, sign random K, just so that you can see. But there's, as far as I'm aware, there's no reason to ever use a random K value. You should simply use the deterministic K value, always. I'm not aware of any advantages to using the random value, and it only opens up the possibility that something went wrong with your entropy pool or with your software and stuff like that. And so I don't know any advantages to doing it that way. So in other words, just use the normal sign method, or just use our higher level convenience classes like message, which are sort of really, if you're just simply signing data, that's probably what you should be using instead. Okay, you guys have any comments or questions about any of that stuff?
No, for me it was clear.
Okay. Okay, well, let me then we're almost finished, and let me just quickly show our documentation for this. So somewhere in here. Okay, so we have documentation on everything that we just talked about. So there's a bit of an overview here along with links to some of the standards. So it's very interesting. I read these standards to prepare this. it was interesting to go back and then read stuff. When you read the DSA one, it's kind of interesting because it's from 1994, which is quite old. And then they say, warning, this is out of date. And that's because it's very out of date. And they have several new standards, every few years they publish a new one. But I only read the oldest one just because it's not like I'm going to use the original algorithm, but it's just interesting to see what they wrote about it back then. Because you can see all the concepts and the original proofs and all that stuff, even though if you actually go to implement it, you should be using whatever the most recent spec is. And that's DSA. We also have the ones for EDSA. So here's the original ANSI standard for DSA. It's just also kind of interesting to browse through this. Bitcoin uses the SECP256K1 curve, which is not described in this document. It lists a bunch of other curves because you can use whatever curve is appropriate, so long as different curves have different properties and things like that are useful for different reasons. The Bitcoin one isn't in here, so it's just a different curve. It's not written in the standard. It is a standard one, just not in that particular standard. And it looks like I have a link to whatever the one. Oh, I just explained. Yeah. Then if you want some background, because I glossed over things like what is a point, go back in and watch the lecture that we have on what is an elliptic curve and what is a point, because that explains the mathematical background here that if you haven't already seen that, you should watch that. And then there's a few examples here of signing and verifying data and using the difference between deterministic K and random K. So, all right, any other concluding comments or questions?
No, I believe it's okay. It's pretty cool to, something that really surprised me when I started using this kind of stuff is that the concepts are pretty advanced, in the mathematical thing. I mean, it's not something so hard, but it's not trivial. It's not the first thing that you learn when you start programming. Yeah. But you have strong abstractions around that, and you can sign in a really secure way in just 2 lines of JavaScript. That's something really, really cool for new users, basically.
Yeah, that's a good point. It's the math is, unfortunately, it's not the same math that people normally learned in school, basically. Unless you go out of your way, you probably haven't studied the math. So that's a little bit unfortunate, but it's not excessively hard to understand if you actually want to read some of these documents and resources and things like that. Especially the prime number stuff it's basically prime numbers and modulus arithmetic, which doesn't take years to learn. You can learn that stuff, by concentrating and reading a book on it, basically. And then the group theory stuff with elliptic curves is kind of in the same category. If you're willing to read a book or two and you can understand the basics of it, but it isn't the type of math that most people have already learned. You do have to go out of your way to actually study it to know it. But like you said, just use the libraries and you don't really have to worry about it.
A comment about that, because I didn't know the math until I meet you guys, and I know that I have that extra help, that it's you basically explain me everything. But it's the really cool videos and tutorials online that you can search that explain you in a intuitive way how the math works. So for everybody that is starting with this, as I did, I recommend it to search a little bit, or ask, Telegram. You're there, so you can answer questions.
Yeah. Well, and then I'm sure we already have those in probably the other elliptic curve video, but we can provide stuff like that again for people that want to dive into the rest of the details to learn the math. Visit us at moneybutton.com, where you can find links to all of the other documentation and stuff. The documentation itself is at docs.moneybutton.com. Read our blog at blog.moneybutton.com. We're accumulating, sort of grouping these videos and documentation together on the blog. And then what else? Our Telegram group as well. So visit us at t.me/moneybuttonhelp. And you can, ask us questions or whatever, and get news about what we're doing and see all the latest links to the rest of the documentation, things like that as well. So, all right, I think that's probably it.
That's it.
Okay, great. Okay, all right, see everybody next time then.